Hey, welcome to part 1 of 2 on eruptions and volcanoes. So in this 2-part series, we're going to be thinking a lot about the internal Earth structure, plate tectonics, and volcanic hazards. And our motivating question here is going to try and relate those three. How does the internal Earth structure and plate tectonics relate to where and how potent volcanic hazards are? And so before we begin the lecture, what I'd like you to do is take 5 minutes or however much time you need to come up with a hypothesis. Where are the most hazardous volcanoes and how does their location and hazard relate to plate tectonics? Now, record this hypothesis somewhere. Throughout this series, you're going to be revising it and eventually turning it in as part of your homework. Okay, so once you have that hypothesis written down, let's continue. We'll start out with the interior of the Earth. We'll start out with this first classification here. So we look at the Earth, it has about a 6,356 to 6,378 kilometer radius. The Earth is not actually a perfect sphere, it's actually more of a squashed sphere that is thicker at the equator than it is from pole to pole. In the very interior of the Earth, we have the core. It is 3,000 kilometers thick, so that makes up half the radius of the Earth, and it is very dense, made of mostly iron, so 80 to 90% of the core is made of iron, which gives it a high density of 11 grams per cubic centimeter. For reference, water is 1 gram per cubic centimeter. Ice is less than that. And within the core, we have an inner core that is solid and an outer core that is molten. If we step outside the core, we get into the mantle, which makes up kind of the remaining half of the Earth. It is 3,000 kilometers thick. So at this point, we're up to about 6,000 kilometers thickness between the core and the mantle. So that's most of the Earth. The mantle, unlike the core, is going to have a lot more silica and oxygen-rich rocks. There's still going to be some iron and some dense magnesium. So the density overall is still going to be heavier than what we're used to, 4.2 to 3.2 grams per cubic centimeter, but considerably less dense than the core. The mantle is mostly solid. I think most of us grew up with the idea of the mantle being completely solid rock or kind of liquidy-ish solid, and it's a mush really is how we should think of it. All right, so taking up just the very outside of the Earth, right, we don't really have that much space left, is going to be the crust. The crust is divided into 2 subsets. We have oceanic crust, so this is what underlies most of our oceans, and it tends to be thinner than what underlies our continents. Oceanic crust is only 5 to 9 kilometers thick, and it tends to contain a lot of silica and oxygen, much like the mantle, but like the mantle has a fair amount of iron and magnesium in it, and this gives it a higher density of 3 grams per cubic centimeter. And this is going to kind of cause it to be a little bit heavier than the continental crust, which, while it's about 10 times thicker, 50 kilometers or more, and it's even thicker when we have really high mountains and get up to 70 kilometers. A continental crust, though, is a bit lighter. It has a density of 2.7 grams per cubic centimeters. And this is because a lot of the iron and magnesium that is present in oceanic crust is not present in continental crust, at least in not as great quantities. And instead, we see more aluminum and potassium in continental crust. And we can compare this, the mass and the volume, to get a sense of these density differences. So the core takes up 32% of the volume or the mass of the Earth, but only 16% of the volume. So its weight or its mass occupies a lot more than just the space that the core occupies. The mantle takes up most of the Earth, 83%. And it still takes up most of the mass, but not quite the same amount, so 68%, right? And this is somewhat compensation for the core being denser. The crust, on the other hand, while it takes up less than 1% of the volume, takes up even less, about half the amount of mass percentage is that? About 0.5% or less of the mass of the Earth. And again, this is reflecting that the crust is much, much lighter than the mantle and the core. So in terms of its weight, its density is going to take up less mass than everything else. And I just like to note that this core mantle crust division is probably one that we are the most familiar with as a general population. And it's a composition-based classification that really has to do with how much iron versus how much silica and aluminum is in each of these layers, and which ties closely to the density. However, as we move forward in the geosciences and in this class, we want to think about the Earth in terms of kind of a process or physical-based composition. And so this gets into our second composition, which is going to be based more on how each part of the Earth behaves and the different processes that go on in those layers of the Earth. So on the bottom here, I've just marked what the former compositions were with the core, mantle, and crust. And so we'll just compare that to this behavior-based classification. The first one is going to be fairly easy. It's the core, which we separate out into the solid inner core and the liquid outer core. So again, they're going to behave differently because they're in different forms. And so we classify them a little bit differently. The next behavior-based classification is actually going to stretch only, part way through the mantle. And this is called the mesosphere. So the mesosphere is part of the mantle, but it's the lower part of the mantle that is under high pressure. And that pressure creates a much more stronger layer than the upper part of the mantle. So the mesosphere is this lower high pressure mantle that's fairly hot and very strong. In contrast to what is just above it, which is the asthenosphere. The asthenosphere, again, is making up part of what we called the mantle before. However, this is a lot more plastic than the other parts of the mantle. It ends about 350 kilometers into the Earth. And it forms kind of the boundary between the mesosphere and the lithosphere, which is going to be the uppermost part of the mantle and the crust from our older classification. And the lithosphere is really what makes up tectonic plates and what we are most interested in as geologists who look at tectonic plates. So the lithosphere is the top part of the mantle and the crust, and it is, in contrast to other parts, it is cool and rigid. So it is going to be harder to just fluidly move around, but it sits on a layer that fluidly moves around. So you can see how this might enable some plate tectonics where you have a rigid layer over a more mobile layer. The lithosphere is about 100 kilometers thick, and again, it makes up the tectonic plates, right? So that kind of switches us to, now that we understand what's in the middle of the Earth, let's look at the surface of the Earth with this view of tectonic plates in mind. So the tectonic plates are the rigid bodies of the lithosphere, and they move around on top of the asthenosphere, which as a more plastic layer can allow some of that slipping and deformation of the lithosphere over the Earth's surface. As the plates move around, they interact with each other, and these give us plate boundaries and lead to a lot of interesting geologic phenomenon that cause things like earthquakes, which we'll talk about tomorrow, and volcanoes, which we'll talk about today. So these are the main plates that we see on the surface of the Earth today. We've got the North American plate that we sit on, and that covers a lot of the North Pole and polar regions. The Antarctic plate that covers the whole South Pole and polar regions. And then some other notable plates. We've got the Pacific plate in the Pacific Ocean, the Eurasian plate covering most of Europe and Asia, the Australian plate, and some really funky interactions between the Pacific plate and the Australian plate in New Zealand, which we can talk about another day. And just a whole lot of other plates, and even more plates that we can't necessarily see on here that are starting to fragment. So these plates interactions lead to three main types of boundaries. So we have areas where plates are moving away from each other. And this is going to cause the plates to grow because we can't just leave a gap in the earth. So as those plates move away, new material is going to form on the edges of the plates. And these divergent boundaries is what they're called. And we can just associate those as divergence is a place where the tectonic plates are growing and moving away. In opposition to this are convergent boundaries. This is where the tectonic plates are coming together or converging. And as they do so, you can't have two plates occupying one space. And so one of them is going to have to shrink or both of them do. And so this is a location where the tectonic plates kind of get eaten up or eroded away and they can get smaller at convergent boundaries. So for instance, if you see any of these plates here that are mostly surrounded by convergent boundaries, those are plates that are disappearing. And if they continue to go through convergence, they may eventually go away. All right, and then we also have places where the plates are kind of sliding past each other without really paying any attention to each other. So there's no need for the plates to be destroyed or to be created. And these are transform boundaries. So a nice example of this is the San Andreas Fault throughout most of California. This is a location where the Pacific Plate and the North American Plate are kind of sliding past each other, saying hello, but not really interacting beyond some earthquakes. All right, so we have all of these plate interactions, but why do they move around? We could just have stationary plates. So it's somewhat of a cycle, but because the plates move around, we have more plate motion is one way to put it. And the first of these feedback processes is ridge push. So where we have a place where two plates are moving away from each other, they often form a ridge between themselves. So an example of this, the Mid-Atlantic Ridge. If you've looked at aerial photographs or bathymetry of the Atlantic Ocean, you'll notice there is a ridge in the center of the ocean, and that is where plates are diverging away from each other and creating new crust. So as the plates are diverging away from each other, we have the asthenosphere from the mantle that is coming up through that ridge and it's creating new material. And that new material is going to be fairly warm because it just came from inside the warm mantle. And because it's fairly warm, it tends to kind of sit a little bit higher in the earth. It's less dense, right? And so that action of having warm, less dense material at these ridges is actually going to push material away from the ridges. In a sense, you're kind of pushing things down slope. You have some, if we were to zoom into these ridges, they often look something like this, where there's actually a slope gradient that pushes material away from the ridge. So this is called ridge push, and it's going to move plates away from each other. So this is a better drawing than the one that I just tried to sketch. So here we have two plates moving away from each other. You've got some asthenosphere coming up and melting and forming new material on the ocean floor. And that is going to kind of create that push away from each other. So one thing to note, you might be asking, why is there melting asthenosphere here and nowhere else? And part of that is because this is an area of thinner crust and therefore lower pressures. So there's less material sitting on top, there's less overburden pressure. And because of that difference in pressure, that causes the asthenosphere to melt and to kind of switch forms from being more of a solid state to being in more of a liquid state. So as that asthenosphere melts, it rises because now it is less buoyant. As it rises, it starts to cool and it forms a new rock. So it forms new ocean floor, essentially. And then that tectonic motion is going to move the new rock away from the ridge, and that allows space for that new rock to form. In a sense too, you can also think of that new rock as kind of like pushing in and making space for itself. Now we get some really cool rock sequences from this. One of my favorite rocks is called an ophiolite sequence, and this is basically a cross-section of this divergent process. And occasionally we get this preserved when plate tectonic processes kind of push it on land. So these ophiolites basically preserve the mantle down to the crust. And what I think is super cool about these is as that melted material, the magma is rising to the surface and cooling, when it meets ocean water, it forms these really cool formations called basalt pillows. So this is an image of some basalt pillows from a seafloor diving expedition. And basically as the magma is coming up and erupting into water, it cools in these rinds. And within the rinds are melted magma, and they kind of form this bulbous shape. And you'll have a little bit of magma coming up into the water, forms this bulbous shape, pinches off, falls, and another bit of magma is released, forms that bulbous pillow, falls, and another one takes its place. So you get like whole seabeds of basalt pillows. This is an example of what that might look like millions of years later. So here's some basalt in eastern Washington, and each of these gray things in here is a basalt pillow. And in this case, they were forming on a slope. So they were forming over here and then falling down and elongating along the slope they were falling on. And all the orange stuff in between is just the lake and ocean sediment that was in between each basalt pillow. So I think those are one of the coolest geologic formations. All right, so moving on from, we've got ridge push, but on the other end of things, we have slab pull. So you've got material that's being pushed away, but at convergent boundaries, you have material that is being pulled together. And the material that is subducted, is what we call it, at these boundaries is actually going to pull on the rest of the plate. So what do I mean by this? If we zoom in to this right side, we have one plate that is meeting another plate, and one of those plates is slightly heavier than the other. And so it is going to subduct under the other plate. And in doing so, it's going to drag the rest of itself under, right? It started to fall. You can think of this almost as like when your tablecloth falls off the table. At some stage, it's okay to have the tablecloth draping off the table, but once you have more tablecloth that's falling off than is on, it pulls the rest of it off, right? And so in a slow process, that's kind of what's going on here. This little bit of the tectonic plate that's falling off is pulling the rest of the tectonic plate with it. So this brings us to the idea of what are convergent boundaries. Convergent boundaries are essentially two plates that collide with each other, and they can do this through three main forms. So we can have two plates that contain ocean colliding with each other. In this case, we have two plates that are made of the same thing, right? So if you remember our first classification of crust, there was oceanic crust and there was continental crust. Oceanic crust is made of a different thing than continental crust. In this case, we don't have to worry about what continental crust is doing. We only have oceanic. And so we have two plates colliding against each other. The one that is older and therefore more dense will tend to be the one that subducts or goes under the other one, whereas the plate that is younger and made of lighter material will tend to override the other plate. As the plate subducts, it tends to melt a bit. You've got greater pressures and greater temperatures with depth, and so this creates magma, and we tend to get a series of island arcs forming on top of these. So Japan is an example of an island arc that grew and coalesced together into a coherent island, and that formed through a oceanic and oceanic crust colliding with each other. We tend to get earthquakes in these areas. And some other examples are Fiji and the Aleutian Islands, which form this really nice island arc that come off of the tip of Alaska, and that really nicely follows where the North American plate is, or the Pacific plate is subducting under the North American plate. All right, yeah, so those are some examples. Okay, and so the other common form is ocean continent. So this would be, well, to take the Alaska example, this would be where the Pacific plate subducts under the North American plate, but instead of there being ocean, there is now Alaska sitting there. So you have continental crust interacting with oceanic crust. And oceanic crust is always going to be denser than continental crust, right? The extra iron and magnesium in oceans is going to increase the density to about 3 grams per cubic centimeter versus 2.6 grams per cubic centimeter for continental crust. So no matter what the ages are, the oceanic crust is always going to subduct under the continental crust. Similar as before, as that oceanic crust subducts, it heats up. You have some alteration and you get magma forming, and that will form volcanoes. So you'll often see a string of volcanoes on the continental crust as a result of ocean continent subduction. So a really nice example of this are the Cascade Range, Oregon and Washington. You've got Mount Baker, Rainier, St. Helens, Hood, Jefferson, all the way down to Shasta and Lassen. This is a line of volcanoes that represent subduction of the Pacific plate under the North American plate, or actually more accurately, the Juan de Fuca plate under the North American plate. And the same thing with the Andes, where you have the Nazca plate subducting. Right, so here's some really nice examples, and amazingly, my annotation of volcanoes lines up with an actual volcano. Right, so these volcanoes are essentially remnant, telling you that there is some subduction going on. All right, and then the last convergent situation, which is less common, is continent-continent. In this case, both plates are fairly light. They have very similar densities, so it's kind of a harder way to tell which one is actually going to subduct. And it ends up being whatever plate is slightly denser ends up subducting. Because both of them contain a lot of continental material, you kind of smush that continental material together and you get really high mountains forming. But you don't tend to get a lot of volcanism. So this is a case where we can get a mountain chain building without a lot of volcanism. And the Himalayas are a really nice example of this. Even though the arc of the Himalayas may look really similar to something created from one of these other two types of convergence, the Himalayas are not volcanic rocks. They're actually made of limestone, which is formed at the bottom of the ocean. Right, so here's a nice example of the arc of the Himalayas. And you can also see behind it the Tibetan Plateau, which is just an example of kind of all of that continental material that is scraped together in that collision. So we tend to get these wider mountain chains. All right, and then lastly, as a result of the slab pull and ridge push, we get convection. So as these plates are moving around, that creates some circulation within the mantle that helps drive even more movement. Okay, so this is going to be the end of part 1. Now that we kind of understand the background of what the Earth is made of and plate tectonics, we'd like to turn to thinking of how those volcanic eruptions are related to plate tectonics. So at this point, I would like you to go back to your initial hypothesis at the beginning and think if you want to revise it in any manner. Specifically with this idea of how volcanic eruptions might be related to plate tectonics. And with eruptions, definitely think of hazards. Okay. All right, well, I'll see you in part 2.